Okay. Today's class, I will briefly revisit the genetic algorithm with the step-by-step algorithm application, and I will continue on this genetic algorithm and by introducing the research project I've done, mostly utilizing the genetic algorithm and fuzzy applications. Genetic algorithm. This is the kind of the backbone of a plan. For example, we are maximizing or minimizing some kind of fitness function, objective function. It is really important not to confuse with the fitness function as well as the chromosome. We are constantly changing chromosome, right? And we are optimizing this fitness function. Okay? Step 1. Choose a suitable string or chromosome length to and the half of the genetic algorithm is done by how do you model your solution space into a form of a string or a chromosome. You can use a real coded one, you can use a binary code, or you can use alphanumeric one, whatever it is. As long as it can behave as a chromosome, then everything is totally fine. The chromosome can also be anything like some pointer, if you use a C++ or something like that. Anything is possible. And assume suitable values for the following variables. This is more correct. Parameter. Population size n, crossover probability, P sub C, probability of crossover, mutation probability, P sub n, and also permissible value of standard deviation of fitness value over population. And let's say so SF and X. You know, in genetic algorithm, we are keeping M population, M different solutions at the same time. And these M chromosomes are actually M different design, and each design has its own fitness value. We can calculate some statistics of this population, the average value of fitness value, standard deviation, whatever it is. And this thing is really important because as evolution keeps going, it's supposed to the average value of average value of the fitness function of the population should increase. However, the standard deviation of this fitness value should be decreased to say that our optimization is converging, right? It's a kind of a rule or standard. How can we tell our optimization value is converging? But how we can check the standard deviation of the fitness value of a population. That's just one most simple standard. And also, you know, the bottom line of genetic algorithm is we are mimicking the evolution process. As you know, this evolution will keep going and going and going. There is no end. So we need this maximum number of generations. I sub max. Okay, that's our initialization step. And step number 2. Generate a random population. Of size M. And as you know, each consisting of a string of length LQ and NQ, and evaluate the fitness values f sub I So we have to evaluate the fitness of every chromosome. Step number 3. Carry out a reproduction or survival process. Step number 4. Carry out a crossover process operation using crossover probability P sub C. And step number 5, carry out the mutation operation using mutation probability P sub n. Step number 6, once again, evaluate the fitness value f sub I of the new chromosome. Also, at this step, find the statistics. Calculate will be more accurate. Calculate. And step number 7. Test for the convergence. Step 8. Test for the generation number. If current generation number is greater than or equal to the maximum, then stop. Otherwise, increase the generation number, then go to step 3. That's the overall picture of this genetic algorithm. I'd like to comment a little caution about this step number 7. We hope that as the generation proceeds, we hope the statistics of the population, especially the standard deviation as well as the average value, will increase or becomes the favorable thing with respect to the fitness function. But that's not always true. For example, whenever there comes a mutation, it can totally mess up the overall statistics of the population. We have no idea what will happen because it's a mutation. So, have to be very careful when you choose this standard deviation as your stopping criterion. If you're taking too strict stopping condition with respect to this standard deviation, then your genetic algorithm will not work. Okay. We can write it as something like this, but they don't usually do. This is not the only stopping criterion. The basic thing is like that. Just think of the evolution process. So you can use your you can use the following stopping criteria. First one, well, if your average value is greater than some value or cutoff line, then you can stop. Or you can say that if the average value's changing ratio is stagnated. For example, if this is the generation, and let's say this is the fitness value. If you plot your average value of the fitness function, it will become something like that. If the change or slope of this fitness function's average value of the fitness function of the population is less than some value, you can stop. The other thing is, if, as I write there, if your standard deviation of fitness value over population is less than some value, then you can stop. Or if the generation number reached some maximum, then you can stop. Or it depends on, if you're more like to take the elitism, someone can agree with this statement. Population will not work. We are only doing things with top 20 elites of overall population as the life is. So if you can take this, for example, if the average value of top 20 or top 10% or top something percent elite population's fitness average value is greater than some value, then you can stop. Or the changing ratio of the top 20% elites is stagnated, then you can stop. Or, the standard deviation of top 20 elites is becomes less than some value, then you can stop. It's totally up to you. Okay? Okay. Usually, this one are, as I mentioned in the previous class, are very computationally expensive because it requires the function evaluation as number of population. If you have M chromosome, you have to evaluate M time for each generation. So you have 100 chromosome, and if your stopping criterion is 1,000 generation, then the number of function evaluation required is 100 times 1,000. 100,000 times of evaluation is required. Very computationally expensive. Okay? The other thing is there is no guarantee that it will converge. Who knows? Okay? The other thing, because evaluation does not require each other's value. Let's assume you are a single chromosome in this population. You don't have to interact with other chromosome in evaluation. You need other chromosome only in survival or reproduction or genetic operations. But in terms of the evaluation, you don't need it. And usually, in real life problem, function evaluation takes much of the time. For example, let's assume this chromosome represents some floating tower design of your floating type offshore wind turbine. Evaluation of the fitness, let's assume it requires one time of WOMIT software run. Then it will require lots of time, and that's the usual case in most of the real problem. So, very computationally expensive. However, it does not require the dependency among the chromosomes. So many researchers are now utilizing this genetic algorithm in parallel computing environment. These algorithms are heavily parallel and can be very easily implemented in parallel software programming. Okay? For example, the function evaluation takes about 1 hour, and you need, for example, 10 chromosomes. But let's assume you have the Linux parallel machine with 128 cores. Then you can divide this evaluation to each of the cores, then you can just run it, right? The interdependency are only required in this chromosome modification, reproduction, and genetic operator. Question? Okay. Usually people like to use the C++ or Java or such a kind of language, and they tend to implement it with the array, because it's a chromosome, a string, array or vector in the standard template library and the like. But people are also trying to memorize the history of the chromosome. For example, let's say this is your chromosome, 10110001. And let's assume evaluation, the fitness of this chromosome takes about 10 minutes or so. But in the generation or population, there are high possibility this specific chromosome will reappear in next generation, right? Who knows? During the mutation, this one can reappear several times, but each of the evaluation will require 10 minutes. So another approach to alleviate this time-consuming approach is keep the history of the evaluation. For example, this chromosome has some value, and you just put this history into your database. Okay? So whenever you come across the same chromosome, you don't do the evaluation. It's a time-consuming. You first refer to your database. Do you have this chromosome already evaluated? If database returns with this number, you don't have to re-evaluate the same thing again and again. By doing this, you can greatly reduce the evaluation time or genetic algorithms running time. Okay? Yep. Okay. I will introduce some of the sample cases. This is the project I've worked as the postdoc researcher at the University of Michigan. My advisor, Professor Parsons, and myself, and the PhD student, one researcher, programmer from computer science engineering department, and this Professor Patel is the professor in computer science engineering. And the title is Intelligent Ship Arrangement. We call ISA, and it's we are kind of showing a new way of initial ship arrangement. You know, initial arrangement is really important in ship design. It determines the weight distribution as well as space utilization, and especially for the warship, it is clearly related to the functionality of the overall ship. So the job is that the U.S. Navy has some kind of already founded database system or product life cycle management system for the U.S. Navy. And our job is to make a module to plug this module, especially for the initial ship design arrangement, and plug that back into the U.S. Navy's PLMS system. So what we did is analyzed the current practice, how currently the U.S. Navy designing a ship, and we systematically analyzed the steps utilizing object-oriented approach. And this one is the solution. For example, the initial ship design, because the rule is very severe to satisfy, the watertight bulkhead and the location of the deck is already predetermined. So we have this kind of zone deck. Our job is to, let's see, there is about 20 or 30 zone decks, and we have about 600 spaces to allocate inside of this zone deck. So first one is allocate 600 spaces into this 20 zone decks first, and then each of the zone deck arrange the geometry of the spaces to make the solution. And in next week we will talk about this fuzzy thing, because the current practice, how the current US Navy officers are designing or allocate their spaces, they have lots of knowledge, but this knowledge is really hard to transform into mathematical formula. For example, the bunker room should be should be very close to the bunker room. The sleeping room should be away from the engine room because of this noise and vibration. But there is no clear formula that distance from this bunker room and the engine room should be greater than 100 or something like that. There is nothing rule like that. Rule says should be the distance is greater from the engine room, then it is much better. That's all. So in order to capture such kind of knowledge, we utilize this function, fuzzy utility functions, and set the constraint in terms of this geometry. Okay, that's the allocation stage. We utilized the genetic algorithm. It's very similar to the bean packing problem we talked about last classes. And this is our fineness function. Okay? However, there are confliction of this interest. For example, let's say there are not a single bunker room. There is a sleeping rooms, several ones, many of them. Officers' sleeping room, and there are many sleeping rooms, but each spaces are competing each other. they want to take the farthest location from the engine room. Okay? They are competing, and this conflict of interest should be managed well. So in order to alleviate, we put some kind of agent system to manage this conflict of interest. So we model several kinds of the intelligent agent to do something, but this is not that important. Okay, once the allocation is done, then we have to geometrically arrange these spaces. This is the plan view of the one John deck, and according to this figure, the 14 spaces are allocated by this genetic algorithm beam packing problem. And there is also the topological constraint, something like this. If this is the stun side, bow side, and this is the stun side, the requirement is like that. Space 9 should be more stun side compared to space 12 or something like that. Or space 6 should be port side compared to the space 1 or something like that. Those kind of topological constraint can be also modeled, and this is our one simple chromosome that represent the solution. We only dealing with the topological solution with this genetic algorithm. Okay? And this is also another fitness value function. And once everything is done, this is just the graphic user interface and the system module development. But anyway, we developed this kind of computer software, and it worked very nicely. We used the Windows machine to run this software, but it takes about 20 minutes or so to generate the optimal solution. This is the fitness value, and this is the x-axis means the number of generation, y-axis means the fitness value. And based on these two, you can clearly see after initial several generations, the mean value, it starts from 0.3 or something. It is just the randomly generated chromosomes fitness value. It increased greatly, sharply at the beginning, but it vibrates again and again, and sometimes it goes under. And you can see this clear peak downward because of the mutation. Okay? And this is the sample solution based on this initial allocation and topology. In this arrangement problem, we take the history of the maximum value as well as the average value. As you can see, average value can be fluctuated, but the best one is keep increasing. Okay? So that's kind of one simple example, and that's the actual result. In each of this John deck, you can see what kind of spaces are allocated in this John deck. And yep. Any questions? Let's resume the class. I will continue in explanation of this genetic algorithm application with Ellie's doctoral dissertation presentation. He was a member of our team in charge of this arrangement optimization, and it's the same thing, but in order to show the more detailed design and application of this optimization, genetic algorithm optimization problem, I brought up this one. This one shows the history of surface worship initial arrangement design. There are many approaches, but this one is utilizing stochastic loop, mostly utilizing fuzzy and genetic algorithm. Same thing. First, do the allocation of the spaces into each of this zone deck, and then do the arrangement inside of this zone deck. First, utilizing the topology, and then using stochastic growth algorithm to actually increase the size of the spaces. That's for the geometry. And after several iterations, then we will approach the solution. This one is about fuzzy, and I will explain the fuzzy algorithm in next Monday's class. This is reiteration of this genetic algorithm. Cost function, fitness value should be first determined, and then selection, reproduction, or survival is done. Variation operation is, in another word, a genetic operator, and iteration, that is the bottom line of this genetic algorithm. It shows the genetic operator. This is mutation. Among this chromosome, you select just one or several genes out of a chromosome, and you just change it. Because this Ellie is a female student, she preferred to use parent and daughter instead of parent and son or something like that. But anyway, parent and child. Swap of two spaces. It could be also a mutation. Okay? And single point crossover is a parent 1 and 2, and selection of the arbitrary location within the chromosome, and you just switched it. That's a crossover. And allocation is done using this kind of chromosome. X1 to Xi, and I is the number of spaces in ships. So, as I mentioned, we had about 600 spaces, so the length of the chromosome is same as the number of spaces in a ship, and each one indicates the location. So if I said X number 3, which means the location of space number 3. So X number 3, if the X number 3 is the 2, then the space number 3 should be allocated in zone deck number 2. That's the design of allocation problem chromosome. Okay, and think of the combination. If, for example, there are 10 spaces in 4 zone decks, then it should be equal to 10 to the power of 6 options. So virtually impossible to do the combinatorial research. Take every possible combination and evaluate and select the best one is virtually impossible. If you increase this one into 600 spaces into 30 zone deck, it's a 600 to the power of 30, which is enormous number of operation, and this fitness function evaluation time, for example, it took about 1 minute or so, then we calculated that it required about 100 years or so to find the optimal one. So it is virtually impossible to find the combinatorial approach solution, and it keeps increasing greatly as the number of spaces and number of zone deck is increasing. Our final goal is to arrange to the optimal arrangement of a aircraft carrier, and the number of zone deck is more than 100, I don't know, maybe 200, and number of spaces are in the number of 1,000 or something. Okay. Allocation objective function, in order to capture this knowledge, know-how in the inside of the Navy, we do this kind of fuzzy design, but I will explain the fuzzy in next class. Anyway, the important thing is this genetic algorithm is quite flexible, so you can utilize it with fuzzy or any other method out there. You can mix and make your new hybrid one with mixed multi-agent, I don't know, maybe simulated annealing, or anyway. The point is, this genetic algorithm is quite flexible. You can mix and make your own new approach as long as you utilize the genes, chromosome, and genetic operator. Okay? For example, there is also approaches like, as I mentioned before, the history of the evaluation could be kept inside of the database to greatly reduce the evaluation time. That's a very simple approach. But you can also make a memory, assign a memory to each of a chromosome. Or going further, you can assign some kind of belief system to each of a chromosome. Belief system, I mean, is somebody said it's a cultural algorithm, which means in genetic algorithm, your gene is just a simple string, the store of information of your genetic information. That's all. But with this belief system, you have your own momentum and direction. I'd like to change in that direction. I don't want to violate this kind of operation or something like that. And it is not proven yet, but some people insist that this implementation of belief system will greatly improve the efficiency of this genetic algorithm. Anything can be possible as long as you can mimic this genetic operator. Okay, that is some allocation example. And this is arrangement in two steps. First one is topology. As I mentioned before, this one means topology. Topology means, in Korean, 위상. So the space 8 should be aston with respect to the number space 7, and space 2 is at the left side of space 7. Those the relative location information. That's a topology, and this topology are modeled as this kind of chromosome. As you can see, this is not straightforward. However, as long as your chromosome can represent a complete solution, then it is chromosome. Okay. Okay. So Ellie's approach is first optimize with this relative location first, and then her approach is then make these spaces to stochastically grow north, south, east, west. If there is a confliction of the interest, for example, this if this space number 5 wants to grow in this direction, space number 6 wants to grow in this direction, then they can collide. But using some very nice modeling approach, this one can be allocated like that. Okay. It's a minor thing with respect to the genetic algorithm. Anyway, it shows how the stochastic growth algorithm represented. And I don't have the actual movie, but in her original presentation, each of these spaces are randomly grow and conflict and alleviate each other's growth and other things. Eventually fill out all the white spaces. That was the point. And this growth algorithm is modeled like that. Some rules to follow and fuzzy, and this shows the geometric constraint. Some spaces, this L-shaped spaces is not good in terms of space utilization. If the narrow point is very narrow, for example, if the space is allocated like that, this is dead spaces. So we want to remove this kind of growth, make this one or make this one. How? Like applying this kind of constraint to the shape of each spaces. Okay, and we want to remove the T-shaped or many other shapes of thing, and each spaces has to have the direct access to the aisles, and this can be also modeled as fuzzy system. So based on this one is optimized into the right side, and the fitness value is increased like that. Based on this Alice model, the 1.0 is the ultimate utilization. So the fitness value cannot go over the 1. So 91% is quite nice approach result. And these white arrows and black arrows means the interactions between the spaces. For example, space 11, the people of the space, in order to do some kind of function, a person should visit the space number 11 and then space number 1. And they have the throughput volume. If the material or human flow between space 1 and 2, 1 and 11 is getting larger and larger, it is better to put these two spaces together to increase the utilization. This arrows shows those kind of human flows, information flows, and material flows. And compared to the original one, you can see that the improved arrangement design. And that's the original one. And that is the optimized one. And she did some test cases to validate the problem. And that's all. Future work, well, it's a just minor thing. Anyway, question about this genetic algorithm? Question, comment? Okay. I will briefly introduce then the fuzzy system. The term fuzzy means nothing more than fuzzy itself. In Korean, we could say 애매모호, fuzzy, right? It is developed to capture this fuzzy information or fuzzy variable or fuzzy things into a mathematical one. And this one is heavily utilized in nowadays white appliances, air conditioner, your washer, dishwasher, refrigerator, and the like. Thing is like that. If your design variable is continuous one, for example, temperature, then no problem at all. You can just measure your temperature and have those exact value inside of your design variable. Temperature T, something something degree, right? No fuzziness at all. But however, sometimes it is not enough. For example, let's take the air heater in this room, and sometimes you can just control the heater like this. If the room temperature go below certain amount, for example, that's the program. And second one is if room temperature go beyond maybe 25, then turn off the heater. Okay? Very straightforward, and this is the simple temperature control algorithm. But nowadays, people need more than that. So, For example, if you implement this kind of algorithm, your actual room temperature, let's say this is 22, let's say this is 25, your room temperature will behave like this in most of the time, which is bad. What we really want is, let's say this is 23, steady state temperature control. Okay? If you reduce this band to make a 23, if you said this is a 22.9 and this is a 23.1, then your heater will just constantly on and off and on and off, and it will be very bad for your machine. Okay, this thing can happen in many home environment. Heater, refrigerator, temperature control, I don't know, maybe when in your washing machine in your home will actually mix the hot water and cold water together to make a warm temperature for your laundry, and all these things can happen. Fuzzy system look the problem a little different, and this one is also very simple. In normal system, we said a statement like that. Temperature is less than some degree. It's a statement. You can decide, is this statement true or false? Right? It's another statement. Temperature in room T is greater than or equal to 25 degrees. True or false? Based on your measured T. So this true or false, true or false. Fuzzy system changing this kind of true, false statement into fuzzy one. For example, and we can model like that. This one actually means if room temperature is cold, then increase the heater. If room temperature is hot, then reduce the heater or turn off the heater. So something like that. Cold, hot. In our model, we said this is 22, this is 25. So we take the portions. So we model our system like this. Until temperature is 22 and below, we said this is cold, 100% true. But what about 22.5? So we take this kind of chart like that. Around 23, it's a, and if the temperature is beyond the 25, we can say that it's a room is hot, 100% true. But however, if it's not totally wrong. It has some portion of truthness and some portion of falseness. Okay? Modeling this, what's the 20? It's a 23.5 degree. So, if we ask in this system, is 23.5 is hot or cold, then it cannot generate answer. But if we ask this fuzzy system is 23.5 is hot or cold, then it will answer, oh, it's a 50% cold and 50% hot. Okay? And in real system, there are many complex things we can define many of the fuzzy information into a single one. For example, this is temperature. And let's say this part means very hot. And this part means hot. And this triangle means medium, cold, very cold. And also the fitness value should be always 1.0. The reason? We said percent. How much this statement is true. So the summation should be always 100%. Okay? So the blue value plus red value at any point should be 1.0. Same is true in here. So by utilizing this kind of thing, we can model the thing into a mathematical formula. As I showed in the previous example, for example, there is a huge implicit knowledge. The experienced designer can do very well, but sometimes it is not very straightforward to mathematically transform those kind of information. We can use this fuzzy. For example, in the worship initial arrangement project, well, people said that, the Navy officer said that this much of distance is nice for the sleeping room and engine room. But if you go more closer than this one, it's marginal. If you closer than more than that, it is unfavorable. But there is no strict numbers or strict rules to capture those kind of things. So what we did is model those kind of know-how and best practices in terms of this fuzzy. If you change this x-axis as the distance between engine room and sleeping room, then you can also model with lots of inner view and experience. This part is favorable, this part is unacceptable, marginal, medium, or something like that. Based on that, you can get the idea of how this linguistic information can be transformed in terms of mathematical form. Okay?